Before we move into the next presentation, it is my great pleasure to introduce our esteemed speaker, Professor Ravikant STG. Professor Ravikant sir is currently working as professor in the Department of Civil Engineering, Indian Institute of Technology, Madras. His primarily R&D interests are structural dynamics, random vibrations, machine learning, steel structures, earthquake engineering, and engineering seismology. He has developed empirical and mechanistic models for simulating earthquakes and their ground motions. He is also involved in developing the seismic zone map of India based on probabilistic seismic hazard analysis. He has supervised over 15 PhDs and presently supervising 10 PhD students. He has published over 200 papers in national and international journals. Professor Ravikant received the National Geoscience Award from Ministry of Mines for his significant contributions to natural hazard investigations, particularly in the scientific study of earthquakes, landslides, floods, and tsunamis, awarded by the Honorable President of India, Srimati Draupadi Murmu in 2024. He has been a member of post-earthquake reconnaissance team, including Natural Disasters Management Authority, that is NDMA, Government of India, which served earthquake-affected areas after the earthquakes. He is a panel member of IS 1893, a code on the earthquake engineering. Now I request Professor Ravikant sir to deliver a lecture on revised seismic zoning and hazard mapping.
One second.
Yes, sir.
So you are able to see the screen, right?
Yes, sir. Yes, sir.
Slides are moving?
Sir, yes, sir. Slides are moving, sir.
Okay. So anyway, so I think, so good morning to all of you. So first of all, I would like to thank Dr. Rajaram and RGM College for inviting me for this workshop on IS 1893. So I think morning, I think Professor Dr. Pradeep Kumar would have given you the overall view about IS 1893. So my lecture, I will be focusing on the zone map basically, where we how it came in the IS code, what is the methodology behind this new seismic zone map of India. So now, as you know, right, so in our zone maps have gone, several revisions have happened. The latest was in 2002, where the India was divided into 4 zones, and these are the PGA values basically. So which so you can see, so the PGS was so for starting from 0.1 G to 0.36 G. So the highest value given in the code was 0.36 G. But when it comes to design, so you will use Z by 2. So automatically, so 0.18 G was used in the design basically. Okay. So now, so if you ask any expert, say who is working in seismic hazard analysis, so about these values, say. So most of the experts feel that so we are underestimating the hazard, and these values are on the lower side. Actually, I will show you the reason also. So then there was a need to revise these values, and then this map was also prepared based only on MMI intensities. So the damage intensities which has been observed for the past earthquakes. So based on that, you see this map has been prepared. So now so there was a so there was a demand is to do this zone map from probabilistic approaches, so that was the thing. So that is how this PSHA maps committee was formed under the BICED 39 to revise this zone map. Now why I'm saying that these values are on the lower side, so if you look at other country maps, say, okay, so like for example, this is the United States hazard map. So here you can see the peak acceleration. So the maximum they go up to 1.6 G basically. Okay. So whereas in our IS code, the highest is 0.36 times Z. And this 1.6 also you will see mostly in this near the faults and others, very high PGA values have been given. Now if you see this Canada zone maps, here they have even gone up to 3G actually, okay, which is being used in design, at some places basically, but other places, so we have 0.35, 0.4G was used in the design. Now, similarly, say if you see this Pakistan's, the seismic hazard map, this one, so they also reported, somewhere around 1G, 1.2G was used, and even in Nepal also, say when they do PSHE analysis, so they get the PGA values around, say 1G, like that they get this thing. Then if you see our neighboring country, this Myanmar, say, so there also 0.85G something is observed in this regions. So if you compare this with our IS code map, so automatically you will see that we have been underestimating, you see, the design values, when you compare to other neighboring countries also, as well as international the standards itself. So, and one more thing, what we see is when the old IS code was, so, when in the code it is written, when you are having a tall building, say that means more than 25 stories. If you are designing a bridge, span is more than 100 meters, power plants, port structures, important heritage structures, they say that the site specific spectrum is mandatory actually. Okay, so these studies have to be carried out, and then you have to compare this with the IS code spectrum, whichever is higher, say we have to use it in the design basically. So here also there was a huge inconsistency was there actually, because when you do site specific studies, they are properly based on some statistical approaches. But when you compare this with our IS codes, which has been done from past damages, so there were so many inconsistencies used to come basically. Another thing is, most of the studies, say NDMA, they want to carry this HVRA study, hazard, vulnerability, risk atlas kind of studies. So there also the old code say it was a little bit difficult actually to integrate the code into this HVRA studies also. So this was also one of the reason why the zone map has to be revised. Now, another thing in, right, in nowadays, you see everybody is talking about performance-based design, in earthquake engineering, where, we don't want one value. See, right now, the IS code gives a zone 5 means 0.36G, but if you want to do performance-based design, say you require the values, for 73 written period, 475, 2475, 4975, 9975. So you should have to give these design values for all these written periods. Then only we can use this performance-based design. So this was also one of the reasons, you see, why this zone map has to be updated, based on this, based on these probabilistic approaches. Now, these are for from the design point of view. Now when you look at the the ground motions, which has been recent earthquakes, many earthquakes have been recorded right now. So if you see this Japan 2011 earthquake, say the maximum PGA at most of the stations was observed more than, you see, 3G, 2.5G, 2G was observed actually. Now in our IS code, you see the maximum value is 0.36G only. Okay, of course you can say that this earthquake magnitude was 9 and it is a very rare. And similarly, say if you see in New Zealand, 6.2 Christchurch earthquake was done. So please know, see here the magnitude is very small actually, but most of the stations, the peak ground acceleration was around 1.5 times, 1.5 times, the gravity. Even the vertical components, they were also higher than, you see, the horizontal. So generally in our design, we earthquake means we do only horizontal, vertical we neglect basically. Okay, but here the vertical is also higher than, you say, the horizontal. So if you see these all these things, you say like international codes design values are very high compared to IS code. Then performance based design, if you want to do, it is difficult to do with IS code. Then if you look at the recent earthquakes, the ground motions, how much they are generating, the values are extremely higher than whatever has been prescribed in the IS code. So the, and then another thing, which scares everybody is if I plot this data, say observed as per year, that is a maximum PG observed cumulative, over the years, if you try to find out. So in olden days, around 1930, 1940, 0.36, around 0.3G was observed actually. Okay, that was, I think, in US, this thing. So then people thought that earthquakes cannot provide, give cannot generate ground motion more than 0.3G. Suddenly, in 1971, San Fernando earthquake occurred basically. So this gave a PG of 1G basically. One times gravity was observed. Then suddenly in 1984, one more earthquake occurred where the PGA was around 2G was exceeded this thing. And in 2009, say in Japan, there was one 7 magnitude earthquake where around 4G was also observed actually. So now if we see, say now this is up to 2020. If you ask me a question, say next, and then in our design also we want the structures to be safe in the future basically. So if I see in the next 50 years actually what is the maximum PGA we are going to observe from the the data point of view. So this upper limit is not known actually. It is very difficult to answer this question. Now you can compare our IS code with this one. Our IS code is the old IS code. The values are around 0.36G, which are very underestimating these numbers itself. So this is the reason, you see, why this new zone map has to be developed here, because of design inconsistencies with performance based and other things also, then data point of view also, then requirement of the engineers also. So this map has to be updated, using this international approaches. So if you see all the international standards, say most of the countries, they develop these type of zone maps based on two approaches. One is probabilistic seismic hazard analysis we call, otherwise is deterministic seismic hazard analysis. Both the methods are widely used in internationally. Now when you are having good quality data, say, so then people use PSHA. Now when the data available is very less, say, you use DSHA, and then you can combine them and you can develop a zone map. So the methodology is very simple. So in DSHA, say, you just identify the sources and some magnitude we assume based on some statistics, and then we select some GMP, and then we estimate the hazard actually. So this is what we call as the DSHA. Now in the PSHSA, we do this total probability theorem. We use this classical equation, right, developed by Cornell in 1967. So where we assume that magnitude, distance, soil all are random variables. So we estimate the recurrence relations, the probability density function for magnitude, probability density function for distance, and then GMP also, and then we integrate, say, all these three probabilities to get this seismic hazard curve. So advantage of PSHA is, you will get a seismic hazard curve where you can estimate your design values for variety of written periods actually. And then if you want to do this, performance based design or seismic risk calculations you want to do, say, so this hazard curve is mandatory. So without this, you will not be able to do the seismic risk also. That's what I mentioned in the previously also. If you want to conduct HVRE studies, hazard, vulnerability, risk atlas or something, if you want to develop, so these hazard curves are mandatory. So what we tried in our to do the new zone map, what we tried to do is we thought of doing from both the approaches and then come up with a new zone map, which understands all these issues. So the first thing was, so we identify all the seismic sources in India. So this, of course, you see, we have a Geological Survey of India, which is a 150-year-old institution, So they have given this fault map, which is available online in Bhukosh website. So total some, 1831 faults have been identified here, basically. And then not only faults in India, faults in Sri Lanka, then neighboring Pakistan and Tibet, say. So this also has been, whichever their official government has published these faults, that also has been included in our analysis, because earthquake which occurs in Pakistan or Tibet also can damage structures in India, basically. So now and other thing what we have done is, because of the data scarcity or the data issues, say, instead of analyzing each and every fault, so we have divided them into 33 zones actually. So we have grouped these faults into zones actually. Like for example, if you see, this is one zone. So this all the faults in zone number 19, say, they are grouped as one group, homogeneous group kind of thing we are addressing. Now, next one was the catalog preparation. This is very important to find out, the recurrence relation or to calculate the probability density function for magnitude, basically. So, of course, India has a very rich history we have, from starting from, all the historical events are there. So there are a lot of studies have been done, basically, in paleoseismic studies have been done. Then from our kings histories, most of the kings used to maintain their autobiographies actually, okay, and they have recorded so many, described many earthquake damages. From that, most of the historical events have been done, and they have also been confirmed by paleoseismic investigations also. So we have collected all the earthquake catalogs, all the earthquakes whatever has happened. And the recent earthquakes, anyway, our Ministry of Earth Science, National Center for Seismology, they release this, every year, they release this earthquake magnitudes, locations, and others. So combined everything, say, up to 2022. So there are something around 68,000 earthquakes have been, included in the catalog, basically. So here we have, more than 826 earthquakes are there. Some are historical, some have been recent things also. So these are some of the sources actually. And the catalog is already available online in NDMA, the website. We have posted this catalog also long back. And then for Nepal and others, say, so we have taken from their government official websites. So once we have the catalog, the first thing is we try to estimate, the recurrence relation, that is a probability density function for magnitude basically. Okay. So this is a standard Gutenberg-Richter law. So which, so where you take log 10 of frequency, say, is A minus B times my MW. So using this catalog data, say, so as already mentioned, we have divided whole area into 33 zones actually. Okay. So for each zone, say, so that is zone number 28, you collect all the catalog data here, and then we estimate this statistical, that is estimating A and B values itself. So here there are several approaches are there, because data is not complete, data is very small, say, so there are several approaches are there. Something like Kijiko's method, Wichet's method is there, and you have to incorporate uncertainty in the magnitudes, uncertainty this one also. So based on that, say, so these recurrence relations have been estimated. So this recurrence relation will tell me the probability density function for the magnitude. Apart from that, it also gives me, you see, the maximum magnitude possible in a given zone itself. So this has been estimated, and these are the values basically. The B value, as already I mentioned here, the uncertainties also have been included. So we will get a standard deviation also. Okay. So if the standard deviation, if it is very high, that means your data quality is very poor. If the data quality is very good, say, the standard deviations will be very less. So we use these standard approaches which are widely used internationally for all these 33 zones. These A and B parameters. Now, and then the mx also has been calculated. The maximum magnitude, possible in a given region also has been calculated here. But sometimes, as already mentioned, when the data is very short and the data, if you don't have confidence, so you have to go by, the expert opinion actually. So this came from, the data. So based on lot of discussions, because we had a committee here, so where experts from NGRI, GSI, NCS, many people were there. So the committee, we have revised some of these values also. Okay, wherever the data, the data scarcity was there. And now coming to this hazard calculations, say, so what we do is there are several methods are there. One method which I did, in the old NDMA reports in 2008. So there we decided that we will go by faults actually, treating the faults as linear and then calculating, the hazard analysis. But then, internationally, because there are many regions where faults are not reported properly. So international people, they do from this circular smoothing, that is just based on the earthquake catalog itself, they compute the hazard values. Then recently one approach came, that is what they call as elliptical smoothing, so which combines faults also as well as the catalog also to find out this lambda values. So we used this approach, and for each zone, say, we have found out this, more or less the focal parameters here, and then based on this fault as well as this one, so we used this elliptical smoothing method, to come up this recurrence values. So these are the numbers actually. So this is what the recurrence ni, of the frequency of this four magnitude I'm showing you as a contours here. So the direction and everything of the contours is influenced by the fault actually, and the values are calculated from the catalog itself. So this has been used. And then, so now the earthquake magnitude probability density function is known, then the distance function is known from this elliptical smoothing. So the next comes is the ground motion prediction equations actually, what GMP, that, like, for a given magnitude and distance, we should be able to estimate the PJ. That is what is required for an engineer basically. So here, as you know, right, in India it is very difficult, and geologically, right, our India is, we have a lot of varieties are there basically. So what we have done is here, the whole India, say, we have divided into majorly three regions actually. One is Himalayan region is there. Then what we call as a shield region actually, which comprises peninsular, the shield portion of this India. Then we have this IGP, Indo-Ganga Basin is there. Then we have the subduction zone earthquakes, where, the deep focus earthquakes occur in this region. So based on this, so we have got this GMPs, an international GMP, and our Indian GMPs also. All of them have been used, and then we use this statistically. There is one, weightages we have to do actually. So what international people they do is, because several GMPs they try to do, the epistemic uncertainty has to be included in our calculations. So for that you have to use some 4 or 5 GMPs, which are tectonically similar regions also, as well as of course regional equation also, and based on the data, say, you try to give some type of weightages actually. So this Himalayan region, we used, these are the GMPs. Then Ganga Basin, say, we used this GMPs, and this equation was specifically developed with the Ganga, Indo-Gangetic Basin data by NGRA. So this was also used. Then in Northeast region, say, that is essential in subduction zone. So these equations were used actually. Now in a similar fashion, say, so we got all the equations for these three regions, and we gave some type of a weightages actually, okay, based on the likelihood function. We have ranked these GMPs and other things also. So we got these numbers, and finally say, so we framed this logic tree actually, okay. So this logic tree is required to and to estimate, you see, the epistemic uncertainty, like here we are using elliptical smoothing. We do by Kijiko's method, what value I will get. If I do by Wichet method, what value we get, and we give some type of weightages. Now in Himalayan region, say, so GMPs also we have, some BSA, this GMP, some 4 or 5 GMPs are there, and these are the weightages actually we give, and then we average all these numbers itself. So this is for Himalayas and Ganga basin, stable continental region, subduction zone. So we have done this, this logic tree analysis also. So now based on this, so finally you see I showed you, this gives you the probability density function for the distance. This we calculate from the, the geological data itself. So this this is a GMP. Sorry, this one is calculated from this GMP here. And whereas this comes with for the distance, and this is a probability density function for the magnitude. And now this value say is calculated from that elliptical smoothing actually. So combining all these three probabilities and then multiply by this one, and you sum up for all the faults, say, you finally get this type of hazard curve actually. So we computed the hazard curve for all possible, like PGA, point to second, entire response spectra itself has been obtained from hazard analysis. And then as already mentioned you, so previously, since we are doing by PSHSA, so you can compute the hazard curve. So that means you can compute values at 73, 475, whatever return period you want, say, you can get these numbers itself. Not only that one, if you are interested, you can calculate M plus sigma, M plus 1.84 percentile. All those numbers also can be calculated from our hazard curves. So we developed several, the contours actually. So this is like a PGA contour for 50 percentile, 73 written periods. Then similarly, say 84 percentile, 73 written period is same. Percentiles are different. Of course, as percentile increases, the values also will increase basically. Now, similarly, say 475 written period, 84 percentile, 50 percentile has been computed here, and then 2475 say. So this 84 as well as this is 50 percentile. You can see the values in Himalayas are around 0.72 G, zero point 0.8 G is observed for 50 percentile. If you take 84 percentile, say, the values are slightly higher compared to 50 percentile. Now, in stable continental regions, the values are around 0.1 G or 0.13, something around, these numbers looks like basically. Now, similarly, say, fourth, this is a 5,000 year return period basically. Of course, as return period increases, the design PG also increases, and this is 10,000 year return period. So these things are very important for important structures like you see the nuclear power plants and other type of structures. Now, similarly, say once we have done the calculations for the entire spectrum, so we did these contour maps for point to second variety has been done. I'm just showing you for point to second. This is what they call in international codes as a short period coefficient. Actual, okay. So this also has been computed for variety of written periods itself. Then other thing what happened was, as already I mentioned you, this PSHA approach it works very nice when you are having good quality of data basically. So like in India, if you see Himalayas, then northeastern regions, say, because a lot of earthquakes occurs frequently, so there, the PSHA will be very nice actually. But when it comes to the shield region, say, in the shield region, the data is very less actual. So some places, like zone number 19 or zone number 18, you will be having, you say, 10 or 15 earthquakes only. So with this 10 or 15 earthquakes, you have to estimate the probability density functions. It will be very, unrealistic, and the standard deviations are also very high. So what the committee recommended was, in the shield region, especially where data is very less, we also do this deterministic hazard analysis also. So this was also done for entire India. This DSHA also, like these magnitudes was computed, the maximum frequent earthquake we call. So this also has been estimated by the committee, and then the focal depth and other things has been assumed. So what we try to do is, from for this also we estimate the ground motions actual, and this will be like a lower bound kind of thing, for our analysis itself. So once again, you see the same fault map has been used, and these are the distances here. If the distance is more than 25, say, that will be recalculated to 25 itself. So we limit these numbers itself. And once again, the logic tree was used actually. But here the only thing is, the magnitude is fixed, but GMPs are varying and distance up to 0 to 20. If it is less than 25, that value is taken. If it is more than 25, so 25 is taken in our calculations. So once again, you see the zone map has been obtained. So these are the magnitudes at each and every grid point. Then these are the distances, and maximum distance has been limited to 25 kilometers itself. So once again, the DSHA map also has been computed actually from this for all the grid point. That is at 50% confidence level I am showing, and of course this corresponds to 2475 because the magnitudes have been scaled such that they correspond to 2475 written period itself. And now, so from DSH also we have contours. From PSH also we have contours. The main thing is all these contours, so they are valid at B-type site actually. That is our BC type site we call. That value is it is valid for 760 meter per second, which computes to soft rock kind of thing. But in India, as you know, right, the surface soil condition is different here. So like in Ganga basin, say there is no 760 meter per second. You will be seeing this huge alluvium actual, okay, deposited by this the Himalayan rivers here. So here, as you know, right, soil amplification will be there, and even in peninsular India, so wherever river mouths are there, you will see a lot of sediments and amplifications can be observed. And even in rocks also there are like sedimentary rock, metamorphic volcanic rocks are there. So volcanic rocks are very strong, sedimentary rocks are not so strong. So this classification also will be there. So right now we have done up to 760. So now if I want to bring these values to the surface level, we should have the the shear wave velocity profiles. All those data has to be there, or the surface the map has to be there. But unfortunately in India we don't have this surface geological maps still are not available here. So what here we did was one simple approach, which we discussed in our committee. So where we grouped the whole India, say, into 4 regions actually based on the geological map, like metamorphic, alluvium, sedimentary, and laterite region. And then luckily some strong motion data was recorded at all these stations itself. So what we did was we collected all the stations, say, in alluvium, all the stations, whatever data we have in sedimentary, laterite, and metamorphic volcanic, and we estimated, taking the as a one as a reference site in on the rock, these amplifications have been computed basically. So this also has been done from deep soil. That is the nonlinear site response analysis also has been carried out to confirm these numbers. And finally, say, so in the committee, after a lot of discussions, we obtained these values like alluvium amplification will be 1.5 to be on the conservative side. So sedimentary rock means 1.15, laterite means 1.35. Metamorphic volcanic rocks are very strong, so there is no amplification. You can take it to be 1, or you can assume them to be at 760 itself. So using these numbers, say, so we multiplied these values, and finally we got this contour map actually. So our contour map is so we have PSHA, DSHA, the maximum of these two values, and then multiplied by these numbers to come up the surface level map for India. So finally, say, so these contours was developed, and a smooth map was developed and given in the presented in the committee. But in India, people doesn't want contour maps, because the contours means the contours are to this side of the road, one value, that side of the road. So there are a lot of implementing this contour map is very difficult in practice, basically. So what the committee, so everybody said that using this contour map, why don't you do something like a zone map kind of thing itself, which will be easy for the design. Not only in India, like in abroad also, say, like especially in Europe, many countries are not going for contours. They also want zone maps itself. Like recently, the Greece, the hazard map also. They have done PSHA, DSHA, everything has been done, but they don't want to use the contours for a design. They want to go ahead with this type of zone maps. So from the contours, how to develop this zone map is a big issue. So here we have done several procedures, like statistically natural breaks algorithm is available. Then so we have smoothened the contours. So using these statistical techniques as spline fitting and others also. So we have come up with this smooth the zone map of India. So right now you can see the whole India has been divided into almost 5 zones basically. So one zone was added, that is zone 6, and we started with zone 2 only to be consistent with the previous zone map. So initially there was a discussion like why don't you start with zone 1, but then we thought people will get confused. So the old zone map started with zone 2. So here also the zone 2 we started, and we have added one more zone 6 in our calculations. So the zone 6 is this Srinagar, Northeast India, Andaman, Kutch region comes under zone 6 basically. Now, in the old zone maps, there were small islands used to be there actually. So they were all coming from some damaging earthquake has occurred. That island will come basically. So that has been removed anyway from the contours itself, and this zone map has come up from this probabilistic, then deterministic, as well as this soil amplification. And now we compared whether the zone map is consistent with the catalogs, consistent with the fault maps. So it is nicely consistent with the fault. So you can see wherever the faults are going down, say, so automatically the zone is higher. Wherever lot of earthquakes you will see, say, there also the zone will be higher actually. See, like for example, here there has been seismic activity has been reported. So automatically the zone map is consistent actually with catalog as well as with this geological map. Also this fault map itself. Now this is the zone map basically. So now we wanted to come to this the response spectrum. As already I mentioned you, we have got this the UHRS, that is we have derived the response spectrum for all the grid points also in probabilistic as well as deterministic analysis. But then in IS code, right, so we wanted to give one easy to calculation, that is like only one response spectra, that is the shape of the response spectra will be same for entire country, only the PGA will be different actually. So this was done in the old code. So this also we wanted to keep up in this new code also. So for that, what we have done is we have calculated the UHRS, that is Uniform Hazard Response Spectra. So what we have done is we have calculated for all the zones actually. So zone 2, so whichever sites are there in the zone 2, say, all the zones the UHRS has been calculated. So we plotted actually all these black lines are all the Uniform Hazard Response Spectra, all the sites which are located in zone 2. So their mean, they have been normalized up to 1g, and then the mean and standard deviation has been obtained. So if I take this 1.65 times the sigma, say, so this blue line comes into picture actually. So this is zone 2 we call. Then now similarly, say in zone 3 also it has been done. So whichever cities are there in whichever sites are there in zone 3, UHRS has been computed. Once again, the mean and standard deviation 1.65 times sigma has been calculated actually. Now this is in zone 4, then zone 5, then zone 6 actually. So based on this smooth and the spectral shapes here, so we got this, we proposed this type of a spectral shape, the green color one which you are seeing here. So and after this blue one is the 1.65 times sigma, which is on the higher side. So based on this, a smooth and the response spectrum shape has been computed actually. And then now what we have done in the code is, as already I mentioned you, so we have to do the performance based design, means you have to give the values at several written periods, say. So we have given these numbers in our code also. So the chart has been given. So where so for each zone, say, suppose for example if it is zone 6, so 75 here, 175, 275, 475, 975. So you will get the values for all written periods actually. So the advantage of this is you can use them in performance based assessment or performance based design. You can use these numbers itself, and you can even compute the derivative of these numbers, and then you can compute your seismic risk calculations also you can do basically. And of course these are the 2475 written periods have been given actually. So now in the code we have clearly mentioned of course, Dr. Pradeep would have already shown you what type of structures, say, what written period you have to use. So that is also has been given basically. And then when it comes to the spectral shapes here, once three spectral shapes have been given. One is for A and B, that is for the rock type set. Previously it was type 1, type 2, type 3. So we just replaced with site class A and B, C and D to be incompatible with international standards. Because all international codes, they use A, B, C, D type of classification. So we also wanted to have the same type of classification for consistency with international codes. So three shapes have been given basically. So C type site, D type site, slightly the long period things will be on the higher side. So the smooth and spectral shape set, this came from our averaging this spectra itself. So the equation is also available in the code where you can use this and you can plot this. So if you want to design any structure, say, so you multiply this with this, the written period, the PGA values, you will get your design spectrum, and you can proceed for your seismic coefficient and load combination, other things you can do from this approach. So the entire methodology, say whatever I mentioned you here, so this methodology is already have documentary is very important. The previous codes also a lot of zone maps have come, but documentation was not there actually. So what we thought was, because in future also somebody will definitely update this zone map here. So what we have done is all the process, say whatever process we have used actually, like probabilistic, what are assumptions, whatever I have done, in deterministic analysis also. So everything we have nicely documented, and this paper is available online. That is a draft earthquake zone map. You can see how what the methodology, where how did we take a decision here, what was the problem. So the whole committee say. So we wrote one paper and then published in this journal. It is available online. So if you want to know more details, you can refer to this paper actually. Now, another thing in the IS code, what we proposed was the vertical component. As already I showed you in the starting, for New Zealand, you see verticals are higher than the horizontal. So the old code say it was giving two-thirds actually. If I want to do this vertical spectrum, essentially tall buildings and others, the vertical spectrum was given as two-thirds of the horizontal PGA. So what we have done here is, since we have all the data in our India, we estimated this V by H ratios actually for Indo-Ganga, all the Indian strong motion data. So we observed that you see these are two-third, 2/3 was not constant, and then it was slightly underestimating at some time periods. So we have proposed this three lines actually. So where you can have so once you derive the horizontal spectrum, say you multiply this by this trilinear thing to get the vertical spectrum. So this is very important for tall buildings, where vertical component is also significant. So this can be used so that you can construct your vertical response spectra. So this also has been given in our code, and of course we have given this for rock, then medium soil as well as soft soil. Actually, that is A, B, then C, and the D type classification. So this also has been given in the code actually. So now other thing was nowadays, as already I mentioned you, people are started performance based design say. So when you want to do performance based design, or even code also specifies like IRC code also, like if you are designing a bridge, span is more than something, then if you are located thing, you have to do time history analysis also in our calculations. So how do we generate time histories is also very big a challenge which has been faced by practicing engineers. So for that, what we have done is we have done two types actually. One is spectrum compatible, this ground motion data, where this also has been done. So for all the cities, so since anyway we have calculated the hazard de-aggregation also has been done. So why don't we do this spectrum compatible with UHRS actually? That the site specific spectrum also has been done here. So what we did was we have done this de-aggregation also, like for each and every grid point or each and every city, say we have done de-aggregation, and then we have calculated this controlling magnitude and controlling distance also for 2475 year return period actual. So at 1 second, 0.2 second has been calculated, and this is a site specific spectrum. So what we did was, a lot of databases are available, India, most of the databases. So we did this spectrum compatible. So we generated several time histories, and then, so this information also has been provided. And if you, and we have also given these contours, like de-aggregation contours we call, the controlling magnitude, then controlling distance, which has to be used in selecting this time histories also has been given for 0 second, 0.2 second, 1 second. So this information also is provided basically. So this is for 1 second, 5 seconds, so magnitudes and distance have been given. And then you can do this spectral matching also has been done for important cities in India basically. Okay, so which population more than 1 million, say we have generated a huge database actually, okay, which are compatible with this the site specific spectra, not with the design spectra. For the site specific spectra, this has been done, all three components, two horizontals as well as one vertical component also. So this also has been done, and this database is also available actually in open source. We are going to post it. So these time histories are spectrum compatible with UHRS actually, that is Uniform Hazard Response Spectra. Now in IS code, what we did was, so these so if we do the spectrum compatible, say, and if they're compatible with UHRS, then that is fine for important structures. But if you want to do for ordinary buildings, say, okay, and then how do we proceed with the time history analysis? So generally, what happens is, the important structure is fine, but if you see common buildings and then the spectrum compatible, also people doesn't want actual. So they want scaling of time histories also was there. So for this, what we did was we have seen to incorporate in our IS code. What we have done is we have looked at all the international codes, what they are doing, in time history basically. So for that, what we did was we first developed a huge database actually, like NGA West 2 database is there, East subduction, Indian database is there, the near source strong motion, Turkey, ESM, New Zealand. So total we are having 15 lakh, time histories are available actually online, and these are one the open source. You can download all these time histories also. So this is a huge data basically. So you can see, so now the recorded time histories itself are available for any combination you want. So definitely in the whole world, time histories are available basically. So now what we did was we looked at all the international code provisions, what they're saying. Like for example, AC7, we saw this code, then European code we saw, then other international codes also we saw, like what they're commenting on, how they're proceeding with this time history analysis. So like, of course, most of the codes, these upper limits, how many ground motions I have to use, whether 3 or 7 or 11, there is no consistency actually. So like for example, if you see Eurocode says, 3 time histories you generate, 3 analysis you put, it is sufficient, Eurocode says. But AC7, if you want, they say that 11 ground motions have to be used, in our analysis. Then FEMA 9C695 says, so this says you have to do 28, near field and 22 far field you have to use, and then to do the time history analysis. So now if you see this AC7, they say that, 7 ground motions employed, and the median structural response should be used as a design. They mention this thing, and they say that if fewer than 7, if we are not able to get the ground motions more than 7, if we are getting ground motion less than 7, they say that the demand should be on the maximum observed values, so like that they say. And they say if we are using irregular or a complex structure, say like tall building or bridge or some important structure, they say that you should do this 11 ground motions is recommended actually. So this is as per AC7 code itself. Then there is one more code is there, that MCER we say, that the earthquake engineering this thing. So here also, like how many ground motions have been selected, some formulas have been given basically. And based on this formula, they say that 11 is a good number for this time history analysis. And the time period range says, so generally when you want to generate a ground motion which is compatible with the design spectrum, and you want this ground motion to be from 0 to 10 seconds, then it is very difficult actually. You will not be able to match, or you will not be able to scale up also. So AC7 has a guideline. It says that the period range, say vibration periods around that range, and if you can match, they say it is sufficient actually. And they also say that upper bound, greater than or equal to, they have these numbers 1.5 times the first measured period. So all these guidelines they have given. So this is for upper bound. Similarly, say they also give lower bound also. How much should be this, the time history, the response spectra compared to the design spectrum. And then scaling also, like how much you have to scale. So most some codes they say spectrum compatible should not be used. You should do directly the scaling of ground motion, like whatever ground recorded ground motion, don't modify its frequency content. You just scale it through some number such that it matches with the response spectra, and that you will do time history analysis also. But how much you have to scale, say whether I have to multiply by 20 times or 10 times. So for that there is some guideline, is the scale factors, up to 0.2 to 5 only has to be used in practical engineering applications. So like this, and then other thing is what response spectra has to be used. So the code gives the design spectrum, okay. But when you want to do time history analysis, you can generate 2 horizontal components also. Bidirectional ground motion is required. So now how do we generate this bidirectional is the issue here. So what this concept is, this rho to d 100 spectrum says. So they say that this should be used in for this scaling of ground motion itself. So what they do is, so you take any ground motions, so 2 horizontals, you multiply by scale factor, and then you compute this rho to d 100, this one, and then you come this with the design spectrum, and you should not follow below this 90% of this spectra. And then vertical is fine. Vertical there is only one component. So this they say you can scale directly with the design spectrum itself. So rho d100 is just a slide to illustrate you. So like for example, if you have ground motions in x direction, then y direction actually. Okay, so what we try to do is we rotate basically. So you rotate these 2 time histories by some angle theta here. So you rotate and you find out the components and you find out this response spectrum. So like this, you vary this theta set from 0 to 180, this angle here, and if for all the directions you compute this, this response spectra, and then you compute the maximum set. So that is what they call as rho to d100. The percentiles you have to do this one. The highest is rho d100, and rho d50 is some 50 percentile it comes. So this should be calculated actually. So here what we have done is, all the ground motions, 15 lakh time histories are available. So what we did was, these are our limits. Like maximum error individual should be plus or minus 10%. permissible mean and target is a plus or minus 10%. Of course, we was ready to come up to plus or minus 5%. Individual ground motion target 10%. The maximum scale factor say 0.2 to 5 actual. So in that, and then since you cannot match with the entire spectrum, so what we have done is we have divided them into some period ranges actual. So 0 to zero point 0.1, then 0.1 to 0.2, 0.2 to 0.3. So we have divided into period ranges, and we try to scale the data which matches nicely in that region. So this is our constraint. So with this, we just, it is just like a hunted, all the 15 lakh time histories say. So we hunted, so like for example, 0 to zero point 0.1, I'm showing you here. So these regions out of 15 lakh time histories, how many of them will nicely match with our IS code spectrum actual. So, and then the error also should be plus or minus 10%. So in 15 lakh, when we search, say only some 4 or 5 ground motions will come in this 0 to 0.1 second. So the same graphs. So this is in log scale, this is in ordinary scale, and this is a road D100 actual. So now in similar fashion, say 0.1 to 0.2, we will get many ground motions actually, because most of the data, lot of ground motions will be in 0.1 to 2. You can see, so this matches nicely in this region itself. And then 0.2 to 0.3. So you can see 0.2 to 0.3, how many of them will match. So here also we get a very good number of ground motions in this range. Then 0.3 to 0.4, you can see as you move on this side, right? So the ground motions average, and it goes towards the right hand side here. And similarly, say 0.5 to 1 second, how many of them will match? Then 1 to 2 second, then 2 to 3 second, then you say 3 to 4, 4 to 5, and like that we proceed with the entire the region itself actually. So finally, say, so we selected 3 in each bin. So total 10 regions are there. So 30 the ground motions have been selected actually. So 0.1 to 0.3 we selected, like although there are many will satisfy this criterion, some 3 best ground motions have been selected in this region actually. So 0.4 to 0.5, 0.5 to 1, 1 to 2, 2 to 3, and 4 to 5 say. So finally, we have proposed this 30 ground motions actually. Okay, so this is given in appendix, in our IS 1893. So these are the mean values, these IS code, and this is our UHRS also. So, and 3 ground motions also we have given here. So the idea here is, so if you want to do any time history analysis in India, right, on the simple side actually, without going to do site specific analysis and other things, you can use this 30 ground motions for performance assessment, and you can see and you can select the ground motions which are close to your that structural natural frequency, and you can do this time history analysis itself. So the entire procedure, these 30 ground motions are available in BIS website actually. I think they have not yet put up, so we are going to post this in the BIS website also. So where you can download this 30 ground motions, and you can use these ground motions to do this the analysis actually. The performance and the seismic analysis of building, time history analysis you can do with this numbers itself. So these anyway road D100. So many ground motions we have given, and all the have been tabulated nicely, they're documented. If you see the annexures backside, we have given the names and the ground motions. You see they have been nicely been filtered to remove all those irregularities. So these 30 are nice ground motions which you can do for seismic assessment and seismic analysis. The time history analysis you can do with these ground motions. So these are some of the samples actual, like horizontal component, both the components, so H1 and H2, similarly say several I'm showing. These are acceleration, these are velocity, then these are displacements actual. Okay, so we have selected very carefully, and we have removed the filtering, everything has been done properly, so that you can do non-linear time history analysis nicely in your calculations. Now 0 to 0.1 I'm showing, some more other samples I'm showing here. So this is how, so this we have given in our IS code actually. So the entire the design spectrum also has been given, which you can use in design. Then we have also given, you see, the time histories where you can do this risk analysis, and then non-linear time history, vulnerability, fragility also can be, you can calculate this using this 30 time histories also. Then one more thing which we have added in the IS code, new code, that is comes in the annexure is the directivity. That's a near field correction factor also has been incorporated in the code itself actually. So what happens is, whatever the IS code, the design spectrum I showed you previously, it is valid in the far field region actually. Even the probabilistic hazard analysis, whatever I have reported previously, it is valid in the far field. That is, if you are far away from the earthquake source, say. So these are perfectly fine. But when you are located very close to the fault, say, then the response spectrum has to be slightly modified actually when you are very close to the fault. So right, so this is one classical figure you see where the effect of the near field has been shown here. So this is for one earthquake in US, so like epicenter was here. So you can see this station and this station. Both of them are located more or less similar actually. To the fault distance is more or less same. But when the rupture is going, say, so this here the velocity will be 136, here it is 43. So there will be a huge increase in this velocity. The energy is rupture is coming to you or rupture is going far away. So then these numbers decreases basically. So this we call them as the pulse type ground motion actually, and there are a lot of papers describing these pulses also. So like Chichi earthquake, say you can see the that Chichi 1999 this Chichi earthquake also. So your accelerations will be like this. So when you try to double integrate, say you will see these type of permanent the ground residual displacement also. So this is what you will see in the near field. And in the acceleration, say you will see this huge the pulse in this the acceleration time history also. So when you look at the response spectra, what happens is when you are in the near field, say, so this peak anyway is a standard actual, okay? You will see in most of the cases, but you will also see one more peak in this region basically, okay? So this is mostly corresponding to the near field. Sometimes you will see these peaks at the long period, say, not only during near field. Suppose if your site is located in a basin actual, okay, like Ganga basin or some type of basin structure, then also you see these type of amplification in the long period actually. But the near field feature, essentially the long period things will get amplified when you are located very close to a seismic source. So now this is how is it for the Chichi earthquakes. You can see this bridge also is it. So this bridge is crossing the fault. So here so the this fault during this earthquake, right? So Chichi earthquake. So this portion has been 7 meter was the height actual. So you can see the buildings are all fine, but because of this fault displacement, say, so this girder collapsed. So this now the same bridge, there are no cracks, nothing has been observed because of this fault displacement, say. So this bridge has collapsed. Now they have joined, so they have repaired this bridge, same bridge only, but the girders have been new girders have been put up. Now you can see this girder was previously it was straight, now it is inclined actually in Chichi region. And then this is also a classical example of a dam located on the top of the fault itself. So Shikang dam we call here. So you can see, so this dam was also crossing the fault here. So you can see there are no cracks, nothing has happened here, but here because of this one, say, so this dam collapsed, and almost 7 meter or 5 meter was uplift observed in this dam, and it has completely collapsed during this Chichi earthquake also. So and this is also you see, so this is a running track, so during that earthquake, say, so this portion has been lifted by 2 meters actually. So when the site is located very close to this fault, say, so it is not only the the spectral acceleration, the fault displacement, all those things comes into picture. And even these are very important for structures which are located to the faults. Like there are many bridges are being constructed in India crossing the faults. Then there are pipelines, say, which are crossing the fault. So this uplift, the fault displacement also becomes very important in the design actually. So now this Taiwan, this all these things they have converted into a museum. So where you can see this near field features itself. So this is also one classical example. You see how to design the dams when they are crossing faults. So what they do is, to account for the fault displacement. So they put a joint, So it is like you see, not a one dam. It is basically a two dams actually. So if there is any movement or something, so this will take care basically of this near field effects. So what we have done here also, like so if there is the original ground motion, so the pulse will be like this basically in this ground motion when you are locating in this near field. So now these pulses people have already calculated, the time period of the pulse with magnitude. Say some equations are already available in international literature, and there is one near source ground motion data set itself is available where you can analyze this data and you can estimate this pulse periods also. And there are a lot of databases are available because so many earthquakes occurred. We have a lot of data recorded very close to the fault. So almost I think 2000 2000 to 2500 time histories are available located very close to faults, and which will show this type of pulse type behavior. So using these things people have extracted, and then a lot of equations are also available in the near field itself. So like you see, and how to simulate also like synthetic to incorporate this pulse. As you can see, say, far field response spectra will be like this, but if it is near field, say, the response spectra, you have to include this peak also, which you can see in this near field region and the long period end itself. So what here we have done here is for our India, say, So we have done once again, we have done the hazard analysis basically. Okay, so incorporating this near field component here. So here the same methodology is more or less the same, elliptical smoothing, all are same. But here the calculations will be two probabilities will be there basically. One is, if there is earthquake and if the source is located in the near field, pulse may also occur, pulse may not occur also. So you have to compute these probabilities. So these are some standard, the equations which are available, internationally, and where you can do the seismic hazard analysis was done. So what we have done is the hazard analysis has been done, and then the probability, say for directivity. So these equations have been developed based on some statistics and some physics behind these phenomena. So for strike slip fault, non-strike slip fault, thrust fault, these probabilities are available. So we have done these calculations actually. So same seismic hazard analysis. Previously there was only one calculation used to be there. Now we have to do both the calculations actually. Suppose a pulse occurs, say how this ground motion hazard curve, how to compute. If there is no pulse, say once again the hazard we calculate basically. Okay, and then we combine these two, including with these probabilities of pulse and probability of no pulse also, and then compute the hazard curve. So this we have tried for all the entire India. We have computed this one. So this is in the northeast region actually. So you can see here. So when there is a pulse, say automatically, you say the long period component automatically it increases actually. Suppose if there is no pulse, the time history, the response spectra will be just like this because of this near field effect, and that also in probabilistic analysis it slightly increases in the long period region. So we computed the ratios also with pulse, without pulse, how much will be the amplification. So these are the numbers. So as you can see, right? So whenever there is a pulse, say, you will see the amplification up to 1.8, 2 also may come up in some regions, especially the periods more than 5 seconds, this range, you will see a huge amplification in this region itself. So if you are constructing a tall building or, structures which have very long time periods, so this, so your design values have to be amplified by this amount itself. So we have carried out for all over the India. Like I'm just showing you northeastern India, because northeast is, several so many faults across here. So northeast, Himalaya, everywhere this hazard analysis has been carried out, and based on this, we have derived one simple, the multiplying factor, actual amplification factor, you can say. So based on all the data set, this is our equation actual. So it is just like a, double, this bilinear kind of a straight line we have here. So where it is 1 in the initial stages, but slightly increases, and when it goes to the long period ranges after 8 seconds or something, so automatically the value will be slightly higher. 10 to 15% you have to increase your spectral shapes. So this is our equation actually, which has come in our code. In the annexure, it is been reported also. So this is a near field amplification factor we call, and this near field amplification factor at 8 seconds you have to find out, and then if you multiply, say, so you will get this nice, the spectral shape. So you can see, so this is the spectral shape. So the black one is per the draft code, that is as per the new IS code, and this is with near field correction factors also. So when you include this near field terms, say automatically you see the values will be on the higher side at the long period ranges itself. So this is how we have incorporated this also in our IS code itself. So so in the IS code is, so we have given the design spectrum, we have given the time histories from both the approaches. One is spectrum compatible also we have given. Then we have also given what we call as, you see, this the scaling also, some 30 time histories also has been given basically. So now this we have also done this displacement response spectra, then energy spectra also we have computed. Of course, this is for the future code actually. So this is not right now, it is not in the code, but maybe after 5 years or maybe the next revision, say, this also we may be incorporating in the IS code, like the displacement response spectra. So this is very important. Right? Most of the things, earthquake is not a force; it is a displacement. So there is other philosophy, displacement-based design here. So for that, the input has to be given in terms of displacement response spectrum, not in terms of spectral acceleration actual. So this also we have computed, and some work is going on, and how to bring this to in our IS code actual. So this is under thing. Maybe you will see these things in the new next revision. Maybe after 5 or 10 years, slowly these things also will going to come up in the IS code. So to just summarize, whatever I have spoken right now. So we have done, I have told you about the seismic hazard map of India. That is a new seismic zone map, basically. Okay. So which is a combination of probabilistic, then deterministic analysis, maximum of these two, and then we have multiplied by this, the amplification factors, some approximation factors computed based on the soil response, also based on the data. So the new seismic zone map has been computed. Then I also showed you the displacement response spectra, PGV say. Okay, so this is going to be the future actually. Okay. Then other thing which I have also shown you in the new IS code is we have also incorporated a correction factor for near field, so we have given this information also. And then even in the time histories also, we have given this near field time 30 near field and 30 far field time history also has been given in the annexure. Okay, we have given the details of all these time histories, and the data will be posted in the BIS website, maybe by this month end, where you can download and you can do this time history analysis also. Then of course I have also the near field ground motion is very important. So right now the pipeline code also is going to come in our IS code. So when you are designing a pipeline, say fault displacement is very important actually. Okay, so it is not the response spectra or the which is governing the design. The fault displacement becomes very important. So this also we have calculated that this table and other things will come in the pipeline code. It will not be in the IS 1893. So this also we are debating whether to incorporate, or in the pipeline code we will incorporate, like for zone 5 say how much should be this fault displacement, so that they can put bearings or something for the pipeline actually. And then future say, as I told you, in the next 10 years or the next revision where it is going to come up say, so you will be seeing this energy based design spectrums, then displacement based design spectrum. So these are all for the future. So you will see these, some of these these concepts maybe after the next revision of our IS code itself. So anyway, so finally, as already I told you, so this work is not my work, So I have done only hazard analysis, but the zone maps say. So there is a committee, the PSHA maps committee, which comes under CD 39.4, and Dr. I.D. Gupta is a convener of this committee. So we have Professor CVR, then D. Srinagesh is there from NGRI, then IIT Bombay faculty is there, Ravi Sinha, then Roshan, atomic energy people are there followed. Then DK Paul, from IIT Roorkee, he was there in the initial, of this zone map preparation. Then we have members from GSI, Geological Survey of India. Then we have from NCS. It is not one person; it is a group. Almost 20 to 30 people, worked hard on the zone map. And we had every week, the meetings, and then finally so many questions was answered, and then we brought this zone map, and finally say Arun Kumar. He is a member secretary for this one, and of course, this project was funded by NDMA for financial support. So NDMA has given us two projects actually. One project was done in 2008. That zone map was done. Then after that, DST also gave us one more project to develop this displacement hazard. Then the third project was given by NDMA itself. So these three projects you followed, right? The output of these three projects is this zone map. And I also acknowledge my students, Bhargavi, Srijaya, at the initial stages. So Srijaya did this hazard analysis, then Bhargavi was there during the code. Then Ravikant, you followed, he did the final touchings of our zone map, and Narsiram, he did this time history analysis, which are there in our IS code, and even the near field correction factors. So we have developed with our research group. So thank you so much, and if there are any questions, I will be happy to answer.
Thank you very much, sir, for your wonderful lecture on the revision of seismic zonation map of our country.